Okay, so this time I think I'm going to start out and do a review of what we did last time about colorless tasks, just because I wanted to go over it again in a slightly reorganized way, because some of these things are going to come up again, and I want to make sure that everything is in place. Remember we had this notion of colorless tasks where you could take someone else's input and someone else's output. And so I think the simplest way to describe what a colorless task is to say that the set of input values determines the set of output values. And that's everything else you can figure out from that. So it doesn't matter how many processes have a particular input value, only as long as there's at least one. And same goes for output. So the number of processes that have a value and who they are doesn't matter. In both cases. So right, consensus is colorless, case-set agreement colorless, weak symmetry breaking where they have to split up into groups is not colorless because you can't change your output to someone else's. And remember, Yoram asked about majority. Majority is not colorless. Here we have a bunch of processes that are voting on something, and then the majority says everybody picks the majority value. And that's not colorless because if you change the set of inputs here is the same, but the outputs are not okay, not the same. So informally, we start out with an input complex with no colors. Problem specification, it's okay if processes start out on the same vertex. Then there's a relation that takes each vertex to another vertex, but unlike before, the vertexes don't have process IDs associated with them. Okay, so this is a part that I wanted to especially go over because we're going to be using this machinery later on. So I want to go over this in a little bit more detail. So by motivation, remember consensus, we have processes here, P0, P1, and P2, and binary inputs. And if you look at all the different ways of assigning binary inputs to three processes, you end up with this octahedron, which is basically a sphere. Think of it as a football. And in fact, it's a straightforward exercise to say that if I give you n+1 processes, all the different ways of assigning zeros, and one of them is an n-dimensional sphere. If we look at two-set agreement, we look at the possible outputs. Yeah, that's not input, that's output. Then actually, no, it is input. So we look at all the different ways we can assign three values to P1, P2, and P3. Then this is all the ways of assigning 0 and 1. It's the same sphere that we saw before. So this is the way of all the ways of defining 0 and 2, and those two edges are the same. Then when we continue this process, we end up with this kind of ring of spheres. And that's not actually a sphere, but topologically it has many of the same properties. And so what I'm going to do now is talk about the properties of pseudospheres, because later on when we start looking at specific examples of models of computation other than the ones we've looked at, everything is going to turn out to either be a pseudosphere or a union of pseudospheres. So this is the notation we'll use. We'll have a set of n+1 process IDs and a sequence of n+1 sets. And these sets are usually going to be simplexes, and their elements are going to be vertexes, but every now and then it's useful to do something else. But for the combinatorial purposes that we care about, all we care about is that they're sets. So nice properties. So vertex consists of process ID and a value from V sub I, an element of that set. A simplex is a collection of vertexes where each process ID is distinct. So we don't want to have any duplications among the process IDs. And this is from big V sub 0, and this is from big V sub I sub k, and so on. So we want the elements associated with each process there. So we're going to do a lot of induction on pseudospheres, and the base case is typically going to be if each of these sets is a singleton set, then the pseudosphere is just a single simplex. There's only one way to assign one value to a process, and that's it. Simplification rule says that if one of these sets happens to be 0, then we don't have any way of assigning a value to that vertex, so we can just throw it out. So we can take the empty vertex, throw out its owner, and for example, here we have 3 processes, but the P1 set is a 0, so that's the same as just taking the 2 processes and the 2 sets. Intersections of pseudospheres have a very simple property. Here we have a pseudosphere over U with sets V sub I. Here we have a pseudosphere over U with sets W sub I. Then if we take the intersection, what we get is, well, a simplex has to be in both of these things, so it has to be some set of distinct processes from U sub I. And each value has to be from V sub I, because it's got to be simplex in here. But each value also has to be a simplex from W sub I, because it's got to be in the other one. And then when you put everything together, it says that each one has to be in the intersection of the 2. So pseudospheres are closed under intersection. You take 2 pseudospheres, you take their intersection, what you end up with is a smaller pseudosphere. And so it looks like this. We just take the individual things. Now notice some of these might be empty, in which case we can then apply the rule for simplifying when we have empty simplexes. And if we want to take the intersection of 2 pseudospheres over overlapping but distinct sets of processes, then we can pad them by putting in null values, taking the intersection and then throwing out the null values. So there's a whole kind of calculus there. Connectivity of pseudospheres is that they're very highly connected. So a lot of what we're going to be doing is showing that if some model of computation, the protocol complexes look like pseudospheres, then they're connected. In particular, we have n plus 1 processes here, then the pseudosphere is n minus 1 connected. I mean, in fact, it's going to be n connected, but all we care about is n minus 1. So the way we do this is we're going to do a fairly straightforward double induction. So first double induction is going to do a structural induction on the set of values that we're assigning. So we say one set of one sequence of sets is less than another one if each one is a subset and one inclusion is a proper subset. So that's sort of the natural definition there. So to prove connectivity, I'm going to do double induction. So first I'm going to induct on the dimension. So I'm going to assume that lower dimensional pseudospheres are appropriately connected, and then we're going to combine them to show that bigger, higher dimensional pseudospheres are connected. And then inside the same dimension, we're going to use this partial order to get connectivity. And of course, everything is going to boil down to the Nerve theorem in the end. So the base case for n, well, what does it mean to be n minus 1 connected? Well, n minus 1, that means minus 1 connected, which means non-empty, which is a pretty easy, so it just says given one process and a singleton set, there's only one way to assign, to match these up. So you have a single vertex that's non-empty. We're done. So for the induction hypothesis, we'll assume that if I have n minus 1, a set of n minus 1 processes, then this is n minus 1 connected. And now we'll do the base case for the partial order. And what that says is that if we have single vertices here, then we know from our earlier rule that this is just a single simplex. And a single simplex is connected. It has no particular topological structure. So there we are. So our induction hypothesis says that if this is n minus 1 connected, for set sequences that are less than the one that we're looking at. So every set sequence that's less than the one that we're looking at, we're going to assume is connected. Then what do we know? Well, because this sequence isn't minimal, if it were minimal, they would all be singletons. But there's got to be some set here that has at least 2 elements in it. And so we'll pick that one, and we'll say, well, let's assume that this is, v sub j's for some j in some index set that contains more than 1 element. So this is our induction hypothesis. So I'm going to define the complex k sub j to be what happens. I'm going to take the pseudosphere, and instead of having the set big V sub j, I'm going to take the singleton set consisting only of that element. And so that's in some sense, a smaller pseudosphere. And particularly, this sequence here is less in the partial order than the one I'm working with. So I know that that's connected. Now, if you look at all the k sub j's, that's a cover for this, because every simplex in here is a simplex of something of one of these sets. And as soon as you have covers, then we can start thinking about the nerve lemma.
So you take the big V sub I,
and then we know we can split it.
Split it into the individual elements.
Yeah, yeah.
And then you use the induction for each of these things and combine through the nerve.
Yeah, yeah, exactly. And the key point is that one of them has to have at least 2 elements, because if it had 1 element, then we wouldn't gain anything by breaking it up, because it would be the same set. Okay, so each k sub j is n minus 1 connected because the set sequence is smaller. Every set in here is contained in the one there, and this containment is strict. So then in order to apply the nerve lemma, these are going to be vertices of the nerve complex, the covering sets. Then we take their intersections over some arbitrary index set j and ask about the connectivity there. But we already know that taking intersections of pseudospheres is already a pseudosphere. It's still a pseudosphere. And then we'll reason about the connectivity of this and then apply the nerve lemma. So this is basically symbol manipulation. So k of big J is the intersection of the k of small j's. And so all of these things, you can move the intersection sign in here, because that's the rule for intersections of pseudospheres. And then since these are singleton sets, their intersection is empty because they're all distinct. So we have a null set here. And so now we can take this p sub I and throw it away, and then just drop this from the list. And so what we end up with is the k of big J is this thing here, where we just throw out that element, and we throw out p sub I. Now the interesting thing is this is as long as a J has more than 1 element, it doesn't matter what a J is. So that all the intersections have a really very simple property, which is actually much stronger than we need to apply the nerve lemma, because it says that when we take the intersections, one thing vanishes and everything else stays the same. And so then but this is n minus 1 dimensional, so that's n minus 1 connected by the induction hypothesis. And in order to apply the nerve lemma, we have to show that it's actually n minus size of J connected, but this is, since J is at least 1, actually it's at least 2, that this is easy, this satisfies that. So we can roll out the nerve lemma. And what it says is that because each of the k sub i's is n minus 1 connected, and each of the intersections is n minus size of J connected, then we know that the pseudosphere, the thing we're interested in, is n minus 1 connected if and only if its nerve complex is n minus 1 connected. So all these arguments with the nerve complex, you take a complicated complex, you break it up into pieces, you say each of the pieces is topologically simple, it's highly connected. So then the only thing that matters is the pattern that the pieces intersect, in which the pieces intersect each other, which is typically much simpler than the one you started out with. And so that says, so we need to show that this is n minus 1 connected. But remember, a simplex is in the nerve complex if the covers intersect. But we've shown that every possible intersection of these, the case of small j's, is non-empty. So that says that every set of vertices in the nerve is a simplex of the nerve. So that just says that the nerve is a single, huge simplex, because any subset of its vertices is corresponds to subcomplexes that intersect, which corresponds to a simplex of the nerve complex. So the nerve complex is a simplex of with this many vertices, and then we take off one for the dimension. And simplexes are connected in all dimensions. So we're done there. So that we put that together, that gives us a proof that any pseudosphere is n-1 connected where U has n+1 elements. So turning something into a pseudosphere makes it highly connected. Next thing is, this is something that we didn't do explicitly last time, but it, I realized that if you explain it this way, then it's much easier to understand what's going on. That the unions of pseudospheres are, of course, not pseudospheres, but they have a very simple structure. So I'm going to look at unions of pseudospheres where every set here is the same set. It works in other cases too, but this is the easiest one to explain. So phi of uv says I'm going to independently assign a value from v to every process ID in U. So this is n, actually it should be n+1 copies. So, so this is, let's say we have a union of pseudospheres where each of these is a different set. So I have remember this is, for each I take some element of vi and I assign it to each vertex in here. So I've taken pseudospheres over possibly different sets, and then I'm going to union them. And the question is, well, what can we say about the connectivity of this? So we have a finite index set. We have the same set of process IDs in every pseudosphere. And we have a distinct set for each pseudosphere. So what I want to argue is that for every k less than n, the complex big K is k-connected if and only if the nerve complex of these things is k-connected. So if you take the union of all of these sets, that gives you a big set, and you look at the subsets of it, that's a cover for the big set. And so it turns out that the connectivity of this depends entirely on the connectivity of the nerve complex of these things. So VI is a set, is an arbitrary set. The union of the VIs is another arbitrary set. But what is a nerve? Well, each V sub I is a vertex of the nerve, and VI and VJ are in a complex if they have a non-empty intersection. And so the pattern in which the V sub I intersect is the nerve. And if the way these intersect itself defines a k-connected complex, then the result of taking pseudospheres over it is k-connected. So if we're looking at, later on you'll see some complexes that are made up of like double unions of pseudospheres, when we talk about real-time models, things like that. And it turns out that they look pretty scary, but they're actually quite easy to analyze because all we need to do is look at the sets that we're taking the pseudospheres over, and we can throw out the entire pseudosphere structure and just look at the underlying sets and reason about their connectivity. And so this has a huge simplifying effect on the entire computation. And this was implicit in what I said before, but I realized that if I explain it this way, then it's actually much easier to understand.
So again, we don't have to look at the structure, just how the sets of values intersect together.
Yeah.
And induce the
Yeah. So if the union is over the same collection of sets, then all we care about are the intersections of these things. And that's a... So how do we know this is true? Well, so K is covered by each of these individual pseudospheres. Because it's, it's defined to be the union, so they cover it. And if you look at the definition of nerve, each pseudosphere here is a vertex of the nerve. So think of taking each of these spheres and replacing it with a vertex. And for every set, now we're going to say, well, this is a possible simplex of the nerve. This is a simplex of the nerve only if this intersection here is non-empty. Well, what is this intersection? Well, we know what this intersection is because we can move the intersection sign inside the pseudosphere symbol. So these are actually pseudospheres where we move these inside. And if that's non-empty, if this set is non-empty, then this whole pseudosphere is non-empty, if and only if. So the fact that we can move intersection signs inside pseudospheres is what gives us the right to use the nerve theorem. And in particular, these, if that's non-empty, then it's n-2 connected. So we get that because each case of J is n-2 connected, and therefore, this much connected, then we know that K itself is K connected if and only if the nerve is K connected. So here the vertexes of the nerve are the individual pseudospheres. The simplexes are the unions of these non-empty unions of these pseudospheres. So the what we've shown so far is that the set of pseudospheres cover the complex. They have this nerve. But also the V sub I cover V, where V is the union of each of the V sub I's. And they have they themselves have a nerve. And so the claim is that these nerves are actually the same. That two pseudospheres have a non-empty intersection if and only if their underlying sets have a non-empty intersection. And so what do we say? We'll say, well, this simplex of the nerve consisting of the pseudospheres is non-empty, if and only if the union of the base sets is non-empty. And that tells you exactly what the
intersection or the union?
The intersection is non-empty. If this intersection is non-empty, then the intersection of these things is non-empty. So we're just in non-emptiness only of intersections. But this gives us this ability to greatly simplify the unions of pseudospheres because we can ignore the pseudosphere part and just look at the underlying sets. So what we end up with is that this union of pseudospheres is K-connected if and only if the nerve of these underlying sets is K-connected. So we can reason about the connectivity of unions of pseudospheres without ever having to think about pseudospheres in some sense. And this will be very useful for the next topic. Okay, so let's summarize what we did with pseudospheres here, just to. So if all the singleton sets, if all the sets are singletons, then we have a single simplex. If any of the sets are empty, then we can just throw them out along with their matching processes. They're closed under intersection. Basically, you move the intersection sign inside the pseudosphere symbol. And they're n-1 connected, and the unions have the same connectivity as the nerves of the base set. And given all of this stuff, we'll be able to move ahead. So I'm going to do some shorthand. So if C is a complex, then I'm going to say that the pseudosphere of U over C is just the union of the pseudosphere over each of the individual simplexes in C. So we've defined a pseudosphere over a set, and a simplex is a set. So if I want to talk about a complex, which is a set of sets, then we just take the union over each of the individual elements. And then what happens is, what I just showed you is that because this is a union, if I take the pseudosphere over a complex, then the nerve of this is C itself. And so the nerve of C is the nerve of the pseudosphere over C. So this means that we can take pseudospheres over complexes but still reason about them as if they were the original complex. So then also we'll need a projection map that takes a simplex in the pseudosphere and throws out the process ID and gives you back the original set. Okay, so now we can go back and do a quick definition of colorless tasks. So we have a colorless input complex, colorless output complex, and a carrier map. And what does this mean? Well, we put pseudospheres over everything. So the colorless task specification is we can write this as a conventional task specification where each process is independently assigned a input vertex from a simplex in the input, same for the output. And then you don't need to worry about this, but this just says that delta and delta star do the obvious things where you go from here to here and then you throw away the process ID. It's the same as throwing away the process ID and then applying the colorless map. Okay, next thing is that we'll do a very brief review of what happens if my input complex is a pseudosphere and I run a read-write protocol. Then it turns out that the connectivity is basically the same. And this will be useful for arguing about the colorless read-write protocols. So if we have a cover for a set k, k sub I for some index set k, then if we apply the protocol complex, so we think about protocol complexes as running an algorithm, but you can also just think of it as an operator that takes in a complex and gives you back an output complex. So if we give it a cover, if we push it through the protocol complex, we still get a cover. And the claim is that they have the same nerves. So since we're reasoning about connectivity in terms of basically in nerves, if we want to prove that this is connected, then it's enough to show that the original complex is connected, given that you have a cover. So here, do some notation. So given k, I'll say if we apply the protocol complex, we get L. Given for each element of the cover, k sub I, we'll have L sub I, and each intersection, k sub j, is L sub j, and so on. This is so that everything fits on the slide. So the L sub I form a cover for L with vertices L sub I and simplexes L sub j. How do we know this is true? Well, L sub j is the union of the L sub little j's. But what that is just applying p to the k sub little j's. And we can move the intersection symbol inside any protocol complex operator. And that's p of k sub a big J. So that says that our notation actually is well defined. So, but that's non-empty if and only if that's non-empty. But these are vertexes of the nerve. And so that just says that the nerves are isomorphic. And so now that we know that the nerves are isomorphic, then we can do any kind of proof we want using the nerve lemma by applying it to the input complex and not worrying about the structure of the protocol complex explicitly, as long as your protocol complex is wait-free read-write memory. So here's a full statement of the lemma. If P is a wait-free read-write protocol, every process writes in snapshots or writes in reads for that matter for some amount of time, and we have some collection of non-empty sets, then running this protocol where your input is taken from the pseudosphere is n-1 connected. How do we do this? Well, we sort of go over the proof that I gave you that the protocol complexes, that pseudospheres are n-connected, and we kind of do it again except we apply p to everything. And so I'm going to do this in sort of high level because it's basically the same argument. So we induct on pseudosphere dimension and partial order, just as before. Base case is, the pseudosphere is a single vertex, and we know that applying the protocol complex to a single vertex is non-empty because it's weight-free. If this were k-resilient, then this would not be true. But this, because it's weight-free, this is true. And -1 connected just means non-empty. So we're done. The base case for the induction is if everything is singleton set, then the underlying pseudosphere is a single simplex. And we proved earlier that if you apply a weight-free read-write protocol to a single simplex, then you're n-1 connected. That was that bit with the critical arguments and so on. So both of the base cases are taken care of.
Do you often use the case where the pseudosphere has several sets?
Mostly in inductive arguments. So for everything, there will be models where you will get several things because what happens is we'll say that some process will get some set of messages. Or what set of messages? Well, it's got to at least include its own. And if the messages are ordered, then it's got to see something that at least includes this, but it might be different for each set. So the first set to go to see might see anything from the beginning to the end. The last set can only see the end. And this will turn out to be pseudospheres over different sets. So it shows up often enough to worry about, but probably most of the time they're always the same set. Okay, induction hypothesis for n says that if we have a pseudosphere over fewer processes, then we're n-2 connected when we apply the protocol complex. So in other words, you could think of this as saying if we kill one process before it takes a step and then run everyone else, then we're n-2 connected. Induction hypothesis for the partial order is that, well, if we have if we're assigning values that are less than the partial order than the ones we're interested in, then each of those kind of subset things is n-1 connected. So let's look at the nerve of the input complex. So just as before, we'll say, so K is a pseudosphere. We know it's not minimal, so some V sub L has more than one element. We'll do the exact same trick we did before. We take K sub L to be the pseudosphere where we replace the big V sub J with a singleton set. And this K sub J is less than K in the partial order. We look at the intersections, and that's an n-1 simplex of the nerve. This is a subcomplex of the protocol complex, but of the nerve of the protocol complex, it's an n-1 simplex. And this is a vertex. And we know that this is n-connected because it's the K sub J's are all pseudospheres. So using the same kind of notation that we did before, where you apply the protocol complex to something, turns K's into L's, and preserves the subscripts. So we know that this is n-1 connected by the induction hypothesis for the partial order. This is n-2 connected by the induction hypothesis for n. So that says that the protocol complex has the same connectivity as the nerve of the L sub J's. But we saw in the previous theorem that these nerves are isomorphic. And we know that this is connected, so that's basically the proof. So this is the same thing we did last time, except I've sort of reorganized it in a slightly more systematic way. Okay, so notation-wise, so remember we said that the input to the colorless complex is a colorless. The input to the colorless task is a colorless complex. We turn it into a colorless complex by taking the pseudosphere, because anybody can take any set of compatible values. And it gets pretty tedious to write this out, so we're going to write that out as P of I star, where I'll always use a star to indicate a colorless complex. And anything that doesn't have a star, you can assume is colored. So if I restate the theorem we just did, it says that for every colorless simplex in here, P sub sigma star is n minus 1 connected. And this is independent of the dimension of I star. Because we're not really talking about I star, we're talking about the pseudosphere over n plus 1 processes of I star, which is n dimensional. But when we say it this way, it's more compact, but bear in mind that this is, this could have, low dimension or high dimension, but it's the dimension of the set of processes that matters for this. Okay, so that's kind of the foundations. So I think what are we doing? Okay, yeah, we can go a little further. Okay, so the fundamental theorem here says that you give me a colorless complex and say, is there a wait-free read-write protocol that solves this? And the answer is that that's true if and only if there's a continuous map that takes the colorless input complex and maps it into the colorless output complex. And of course, it has to agree with your problem specification. So that says that whether a protocol exists depends on whether a continuous map exists between these underlying spaces. A continuous map? Oh, so you take the complex, take the input complex, which is defined in a combinatorial way. You turn it into a point set in space. You do the same thing for the output complex. And then you have this delta star that says, if you're in this region of the input, you can end up in that region of the output. If you can find a continuous map that agrees with that, then protocol exists. And if you can't find a continuous map, if there's a hole in the way or something, then there's no protocol. So it's a way of sort of linking together this kind of discrete combinatorial algorithmic programs unfolding in time world with this sort of continuous world from analysis and so on. And this is going to be useful later on because that means we can pull out theorems about continuous maps and use those. And so we can be opportunistic about moving from discrete to continuous and then back again, depending on where the most convenient theorems happen to be. Okay, one direction, suppose I have a continuous map, turn it into a protocol. So the theorem says there is a wait-free read-write protocol if and only if there's this continuous map. And so the direction we want to go in is if this is true, then that's true. So we're going to argue for all of these things when you want to build up a continuous anything, then you argue by induction on the skeleton. So the skeleton is you take a complex and then you look at all the simplexes of dimension below whatever level you're interested in. So this is the one skeleton of that. This is the zero skeleton of this and of that, and so on. So the proof strategy is I'm going to build continuous maps on the d-dimensional skeleton until I reach the top level. And so the base where d is 0, all I need to do is this is just a set of vertexes. So I pick, for every vertex here, I just pick any vertex in the image of P of V. So say if I take V and I run P, then I'm going to end up with some, actually only one vertex. But you can pretend that there's more. You just pick any vertex over there. That's your definition for the in dimension 0. So then for the induction hypothesis, let's say I built this up to dimension d minus 1, the d minus 1 skeleton. Now I want to define the map up to the next higher skeleton. So what I can say is that, well, if I take the boundary of this d simplex here, well, that's actually a sphere, topologically speaking. If I take a solid triangle, I'll look at the boundary, that's a circle. If I take a solid tetrahedron, look at the boundary, that's looks like a football. And What do we know about that? Well, we know that any continuous map of the sphere can be filled into a continuous map of the disk because it's connected. That's why we prove all these theorems about conductivity. So because this is connected, we can extend the map. And what we're doing is we're extending the map over the interior of each of the boundaries. So the extended map on each simplex it agrees because they only overlap on the boundaries, and we haven't changed that. So each of these individual extensions is basically compatible with the others. So this gives us a map in the next higher dimension. So we just keep going until we get to the top dimension. So we constructed a map from the colorless input complex to the protocol complex. And we know, I mean, what does the protocol do? Well, you run your protocol and everybody ends up on a vertex of the protocol complex, and you look at it and you say, oh, I know now I should decide 0 or 27 by applying this simplicial decision map that takes your vertex on the protocol complex and gives you an output vertex. And we can turn that into a continuous map using the tricks with the barycentric coordinates. And then when we compose these things, what we get is we get the map that we're looking for. Actually, yeah. So, so given the protocol, we've defined a map. So going the other way is, we just flip the two things. Say, if there's a continuous map, then we want a protocol. And this is just going to be an application of the simplicial approximation theorem. So we're going to use this kind of subroutine where, let's say, if everybody starts out, we'll start out with a colorless input complex. I've only drawn one triangle here because I'm lazy, but think of it as a whole complex. And look at its barycentric subdivision, where we divide each face in the middle and then, looks like that. And a bunch of processes come in and each one starts out on a corner. Because it's colorless, you can have more than one start out with the same value. And the goal is that at the end, we want them to converge onto a simplex of the barycentric subdivision. And it's okay if they all go on a single vertex. It's okay if they go on an edge or on a triangle, but they have to be on some kind of simplex over here. And so the claim is that this is fairly straightforward. I'll give you a protocol to do this. So here, let's assume that we have, each process has a location in shared memory. And you can write and snapshot. So each process starts out, it writes its vertex to the shared memory, and then it takes a snapshot. And in this particular execution, the red process sees only its own vertex. Blue comes along, it does the same thing. And because the snapshots are atomic, they're ordered. So if I run together with someone else, then either I see a superset of what they saw, or vice versa, or we see the same thing. But they have to be ordered with respect to one another. And so here, what happens is everybody here sees a set of vertexes. But these vertexes that they see is actually a face of the input simplex. Because each vertex is somebody's input. The inputs have to lie on a simplex. So red sees this vertex, blue sees this edge, and yellow sees this triangle. And the idea here is that they're ordered. So this is contained in this is contained in that. Now, each vertex, each face that they see is also, if you go to the barycentric subdivision, is a vertex of the barycentric subdivision. So a lot of what we do here is we'll build up something in one complex and then say, well, this complicated thing is actually a vertex of a different complex. That's what we did with the nerve theorem. That's what we're doing here. So we're saying the face of the triangle is actually a vertex of its subdivision. So instead of saying we saw a face, you can say, well, I saw this vertex of the subdivision. I saw this vertex of the subdivision. I saw this vertex of the subdivision. And because the faces are ordered, what they actually see is a simplex of the barycentric subdivision. because the definition of the combinatorial definition of the barycentric subdivision says it's a chain of faces that are included in each other. So that says that this, you write your value, take a snapshot, is a solution to this barycentric agreement task. And of course, if it's worth doing once, it's worth doing n times. So by repeating this protocol, you can take, here we've done 2 subdivisions. And, here everyone can start out in one, and then they can converge on a simplex of the nth subdivision just by doing the same thing n times. Okay, so now that we have that, I'm going to show you how to go from a map to a protocol. So we're given a continuous map. Then what I'm going to do is I'm going to take a simplicial approximation of that map. So now I have a map from some subdivision. I've only drawn one, but this is actually, the simplicial approximation theorem says there exists an n so that if you subdivide it enough, you can always find a simplicial approximation. And now that we have this combinatorial object, this map, we can turn it into an algorithm by having them run barycentric agreement to end up on a single simplex over here. And then we can apply the simplicial map, which means they end up on a single simplex over here. And that's our algorithm. So given the continuous map, we find the simplicial approximation. We know what the big N is after we've done that. Then we run big N rounds of barycentric agreement to converge on a small triangle. We push that through the simplicial approximation, and there you are. And the proof doesn't matter how many processes start on each vertex. So that gives us both directions of the proof, the necessary and sufficient part. So, so that's our theorem. So the applications that we did, I'll go through this quickly, and then we can take a break. You could say, well, what if we only want to tolerate t failures instead of being a weight-free? So the algorithms I gave you here doesn't necessarily work with t failures because applying a protocol complex to a single vertex doesn't mean anything in that model. You have to have a certain number of processes to run. And so motivation is sometimes you have architectures that provide stronger things. So as a first, we'll deal with this systematically in the next set of lectures. But as kind of a throwaway line here, we'll say, well, suppose that we have weight-free read-write memory augmented with a black box that does case-set agreement. There are various somewhat suspicious motivations for this. But the basic theorem is that this has a weight-free solution in read-write plus black box protocol if there's a continuous map from the skeleton. So instead of having a map from the entire thing, we can throw out all the high-dimensional simplexes, and this makes it easier to solve because there are strictly fewer constraints on the map. So we're lowering the condition from the entire complex to the skeleton. And so we can say, well, what does it mean to do case-set agreement with fewer than k processes? Well, without loss of generality, we'll say you get your own value back. And so that's the same as read-write. So in one direction, all we do is we do the same construction we did before, except we stop when it gets difficult. Because with fewer than k, with k or fewer processes, it's exactly like a read-write protocol. And so we do that. So this is the exact same construction, except that we stopped at the skeleton. So here, for example, we're looking at the one skeleton for two-set agreement. And now what we're doing is we only need to look at the boundary here, and we can put the boundary, say, around this hole here, which we couldn't do before. So this actually buys you some computational power to have this black box. And so what we'll do is first step now is we'll run case-set agreement. What does case-set agreement do? Well, it allows everyone to jump to the k-1 skeleton. And once we've jumped to the k-1 skeleton, then as before, we look at the simplicial approximation. We run barycentric agreement on the simplicial approximation. We apply phi, and then we're done. So it's the same thing with a little bit more stuff. Okay, so that's that theorem. So the last thing we did was we looked at decidability. If I give you a task specification, which after all is just a finite simplicial complex, the input complex is finite, the output complex is finite, the relation delta is finite. So you could write it all down on a Turing machine tape and then say, is there a Turing machine that decides whether a protocol has a solution in read-write memory? And by implication, other models. So then turns out that whether a protocol exists for read-write memory for 3 or more processes is undecidable. Read-write memory in case-set agreement is undecidable if k is greater than 2. And here is the basic approach. So we start out with a complex. Going to define the notion of a loop, which is just a path, a one-dimensional path around, that starts out at vertex, comes back to that vertex. I'm going to pick 3 rendezvous points. And the input is, every process starts out with one of these rendezvous points as its input. So imagine that they all start out with the same rendezvous point as the input. Then they have to stay there. Everyone has to decide that value. If they start out with 2 distinct rendezvous points, then the requirement is that they have to converge on a simplex on the path between those 2 points. If they start out with all 3 values, then they have to converge anywhere on the complex. So this problem exists in order to be reduced to a problem known to be undecidable. Key idea here is contractibility. A loop is contractible if I can continuously deform it to a point. This loop is contractible. This one is not contractible. So what our theorem says, remember it says, so this is, the input complex is really just a single simplex where each vertex corresponds to a, one of the rendezvous points, because everybody starts out on, the processes, they might start out at 1, 2, or 3 different values. We don't care how many processes there are. We know that there's a continuous map from this complex to the output complex, if and only if there's a solution. So, but what does that mean? Well, it means that this loop here has to be contractible, because I can take this loop and continuously deform it, and that induces a continuous deformation to a point over here. And so the question, is this problem, does this have a solution in wait-free read-write memory, is equivalent to saying, is that loop contractible? And, but loop contractibility is undecidable for finite complexes. And that's a kind of a standard result. So it says that it's undecidable whether a task has a protocol in wait-free read-write memory, for 3 or more processes. If I give you a case-set agreement for k larger than 2, well, that's the same thing because the loop is just one-dimensional, and the skeleton tells you whether it's contractible. So it's undecidable for k larger than 2. Other models, if you have a case less than 2, then it's solvable. Because if it's k equals 1, then there's always a solution. And that's what follows from universality of consensus. If k equals 2, it depends on questions about path conductivity, which is decidable. So, okay, so that's the review of what we did last time. Let's take a break, and then we'll start something new after that.